Okay. Uh, so good morning to everyone. So yesterday we learned analysis of bars of varying cross section. So as well as we learned with the uniform cross section, the members which are subjected to different loads at different locations. But today we are going to learn about the analysis of bars of varying cross section. So here you can see in the diagram. So this is the one member, so which has some cross sectional area A1, and second member, so which has length L2 and cross sectional area A2, and third member has a cross sectional area A3 and L3. Its length is L3. So in previous case, the member is subjected to force at the extreme end as well as at intersecting points of two members also. But in this configuration, in the present configuration, we have only one force, so which is acting at the extreme end. It means that the same amount of load is acting on member 1, member 2 and member 3 as well. Now here, so already the theory relevant to this, so we learned in the previous lecture. So I will take the overview just. Say this is the force acting on a member. Its length is L1 and A1 is the cross-sectional area. So you can compute the deformation. So delta L, change in length in member 1 is equal to, so as we know, P1 PL by AE. P is the load, amount of load acting, L1 is the length, upon cross sectional area of the member 1 and Young's modulus of this member 1, E1. So this is the definition for determining delta L, change in length. Delta L1 can be computed by using this formula. Similarly, if you want to predict the stress in member 1, stress is equal to, so here the P is the load, so which is acting on the member, upon area A1. And similarly, strain in member 1, same formula, delta L1, change in length upon original length of the component L1. So, or you can write strain is equal to sigma is equal to sigma into sigma by E. So this is not into, so this is not there, sigma 1 by E. So like this also you can compute the stress, strain and deformation of a particular member by using these formulae. Similarly, you can apply same formula for computing stresses in the component. So same, Young's modulus E is equal to stress upon strain. So this is equal to okay. Similarly, you can compute here Young's modulus of the material if you know stress and strain. Same formulas were applicable here also. Stress, strain and displacement can be computed in the member 2 and similarly member 3. So if you want to compute a total elongation in this member due to application of this load P, so that can be computed by using this formula. Delta L is equal to delta L1 plus delta L2. So this is delta L2, deformation in member 2, and delta L3, deformation in member 3, is equal to P by E, because we are assuming that this entire structure or entire members are made up of same material. So they have a same Young's modulus. Young's modulus for section 1, section 2 and section 3 is same, and the same load is acting over section 1, section 2 and section 3. So therefore here we are taking this as a common. P by E is equal to L1 upon A1 plus L2 upon A2 plus L3 upon A3. So this is the formula used for computing total elongation in the member, which is made up of same material and which is subjected to a same load, but it is having a different cross-sectional area and different length. So for this configuration, so this formula is applicable. Let us see a numerical on this. See here, an axial pull of 35 kilonewton is acting on a bar consisting of 3 lengths as shown in figure. If the Young's modulus of the material is equal to 2.1 into 10 raised to 5 Newton per mm square, determine stress in each section and total extension of the bar. So here it is asked, what is the stress in the member and total elongation. So that we have to compute. Just now we have gone through the formulas used for computing stresses as well as total elongation. Now, first of all, you should keep the approach, proper approach for solving the problem. So if any problem is given, first of all, what you have to do, so you have to read the problem thoroughly and understand it first. Don't be hurry in answering the answer to the question. So always before answering, you read the question thoroughly, understand it, and then the second step, write the given data. So you don't forget to write given data. Even if you have made certain mistakes during reading the questions, so if you are writing once again that given data, there you will get the clarity. So that's why it is must you should write a given data. So I have written given data. So this is the load pull. P is equal to 35 kilonewton. So this kilonewton is converted in terms of Newton. So it is multiplied by 1000. 35 into 1000, you will get 35,000 newtons. It is converted in terms of Newton. So in question it is 35 kilonewton. So this is in terms of Newton. Then Young's modulus E, because Young's modulus E is same for all the sections. So therefore, E1 is equal to E2 is equal to E3 is equal to E. So that is equal to 2.1 into 10 raised to 5 Newton per mm square. So here again, area is given. Say section, diameter of this section is given 2 centimeter. So D1 is equal to 2 centimeter and D2 is equal to 3 centimeter. D3 is equal to 5 centimeter. So this is given. First you write the given data, D1, and L1, L2, L3 is given. L1 is equal to 20 centimeter, L2 is equal to 25 centimeter, L3 is equal to 20 centimeter. I think I have written this. No, it is not written. So if you have to write this, I will write here by using some other color. Say L1 is equal to 20 centimeter and L2 is equal to 25 centimeter and L3 is equal to 22 centimeter. See here, one more thing you have to remember. First data, this is P is written in terms of Newton and E is written in terms of mm. But here you see diameter is in terms of centimeter. So always you have to put, whenever you are writing the given data, you write given data in single unit. So here you are representing in terms of mm. So means, so again you have to write this D1 is equal to 2 centimeter means this is 20 centimeter. D2 is 3 centimeter means, sorry, 30 mm, 5 centimeter, 50 mm. So you have to write this here itself in terms of mm. Similarly, you convert this length is also in terms of mm. So this is 200 mm length and this is 250 mm and this is 220 mm. So always you put this data, because further calculations, it helps you a lot. Always you have to present in a single unit. So this is the primary task. So the rest of the thing becomes very easy. So first of all, you have to write the given data. Whatever given data, you write appropriately and convert this into a single unit, either mm, centimeter, meter, whichever you feel convenient, but all data should be in single form. So this is the first task. And the second, okay, I have written here for section 1. So L1 is length 20 centimeter. It is converted in terms of mm, and diameter D1 2 centimeter 20 mm. Cross sectional area A is found, because calculating stress we need A. A is equal to pi by 4 into D square. So it is written in case of 100 into pi mm square, or you multiply this 100 into 3.14 mm square. So you can write like this also. Similarly, it is written for section 2. So this is given data. L2 is equal to 25 centimeter 250 mm D2 and A2. Similarly, so this is written for section 3. So we have written these things in a proper way. This is expected. So always you are solving the problem, you write the given data in a proper fashion. So then only you will get the appropriate results, and it becomes easy to calculation. Once you have written the required data, because we need A, already area we have calculated here, and the remaining dimensions we have written in a single unit. So this is the first step. And second step, now it is asked to compute the stresses in each section. Now it's easy. Stress in section 1. This is stress in section 1. Stress in section 1. So that is load. So P upon cross sectional area. So area is already we have computed in previous slide. A1 is equal to 100 into pi. So you divide this. P is in terms of 35 kilonewton upon 1000 pi. You will get 111.408 Newton per mm square. Similarly, stress in element 2, force upon area. So you will get stress. In section 3, stress is equal to P upon area, corresponding area. Area of this section is 625 pi. 32,000 upon 625 pi is equal to 17.85 Newton square. So thus, so these members are subjected to stress. So you can see here, so one conclusion we can draw from the whatever results obtained. You see here, the maximum stress is acting in member 1. Here you can see the maximum, and minimum stress in member 3. So means the cross section, because it is subjected to same amount of load, cross sectional area is smaller, so therefore more amount of stress is acting on member 3, and here cross sectional area is more, the less amount of stress is acting in section 3. So here cross sectional area A1 is inversely proportional to the stress. As the cross sectional area increases, stress in the component decreases. So this is evident for variation of cross section with respect to stress for same amount of load. The next given point is to compute the total elongation. So total elongation for a component from total elongation so can be computed by using the relation total extension delta L is equal to delta L1 displacement in section 1, displacement or deformation in section 1. So this is section 1, delta L1. So it is written here. So delta 1. So on application of this load, so it will deform by a distance of delta 1. And the second, delta 2. So deformation of this member, delta 2 and delta 3. So the individual deformation of each members you compute. And then total elongation is equal to, as we discussed in the previous slide, if the same load is acting over entire member upon Young's modulus of the material is same for all the three cases. So then, so you can write P upon E into L1 by A1 plus L2 by A2 plus L3 by A3. So this is the standard formula. Directly you can use. Otherwise, you can write P L1 upon E into A1. So independently for all the three sections and sum together, whichever way you find convenient. So you can write, and now you substitute the corresponding values. So we know the value of P. P is equal to 35,000 kilonewton, and Young's modulus is 2.1 into 10 raised to 5. And length, corresponding lengths are, see, 20 centimeter, 200 mm, 250 mm, 250 mm second, third 220 mm, and divided by area we have computed already, we have written here, see here, 100 pi for second section, 225 pi, third section 625 pi. So I'm substituting and simplifying these values, so you will get 0.183 mm. So this is the amount of deformation so which occurred in the member. This is the total elongation. So total elongation of this, all the three members, extends in the direction of load by a distance equal to 0.183 mm. So this is how you can compute the stresses and elongation of this bar or extension of the bars. So now we will see one more numerical, so which is of a little bit different category. Sorry, this is also the same category. So here it is, one end is fixed and it is having a two members, one and two members here also. So I will read the first question and then so we can understand the problem. So a steel rod 20 mm 5 and 0.8 mm long is rigidly attached to a aluminum rod 40 mm 5 and 1 meter long is as shown in figure. This combination is subjected to a tensile load of 40 kilonewton. Find the stresses in the material and total elongation of the bar if E for steel is 200 GPa and E for aluminum is 70 GPa. So here there is only one difference between previous numerical and this numerical. So in the previous numerical, all members or sections are made up of same material, but here in this problem, so both sections are made up of different material. So this is a one kind of composite material. The one part is made up of one material and other part is made up of different materials. So this problem belongs to a composite material, different materials, and previous problem with homogeneous material, same material. This is the difference between previous problem and this problem. So and the rest of the things are same. So first step, so always you remember to write the given data. So I have written here given data. So load is given. So here it is, load is given, say 40 kilonewton. Same 40 kilonewton is written here. So always we are presenting the Young's modulus is Newton per mm square. So there is no kilonewton. So therefore, so we need to convert this in terms of Newton. So I have converted this in terms of Newton, 40 into 1000, 40,000 Newton. And second, so material properties were given. So Young's modulus for steel, 200 GPa. So Young's modulus for steel is 200 GPa. So if you are converting GPa to Newton per mm square, so you have to multiply this with 10 raised to 3. So it will be converted in terms of Newton per mm square. I have converted this in terms of GPa into Newton per mm square. You remember, so whenever data is given in terms of GPa, so you multiply that GPa value so with 10 raised to 3. So it will be converted in terms of Newton per mm square. Similarly, The Young's modulus for aluminium is given. So it is 70 newtons per mm square. 70 Newton per mm square. This is 70. Again, we need to convert this into a desired form. So that is in terms of Newton per mm square. So it is in terms of GPa. You convert this GPa into Newton per mm square by multiplying 10 raised to 3. So it is converted. And third is, so we need to compute. So the data is given in terms of diameters. So here 25 and 45. So both have dimensions in mm. So here it is given 20 mm and 40 mm. First of all, we have to convert this in terms of area. Area of steel pi by 4 into d square. So that d is equal to 20 mm. So it is substituted. And area of aluminium cross section or aluminium bar is equal to pi by 4 into 40 square. And lengths are given. See here, I have written in diagram in terms of mm, but here it is given in terms of meter, 0.8 meter. So here it is 0.8 meter. Always rest of the values we have presented in terms of mm. So here also we have represented in terms of mm. So therefore, so we need to convert this in terms of mm. So 0.8 meter is converted in terms of mm. So 1 meter is also converted. So this is important. Always you be cautious about whenever you are converting the data. So you write data in an appropriate way. It will take 1 minute, but it will reduce the risk of getting wrong results, as well as, so whatever steps you have done rightly, so you will get the perfect answer. So for that, this stage is must. Once you have written in an appropriate form, the rest of the things are similar. So for getting the solution, first of all, you write the free body diagram for first section. So and this section is subjected to 40 kilonewton. So the force is acting on this member is in this direction. So we are assuming this is rigid in nature. So there is a resistance to deformation which is acting in opposite direction. So that's why 40 kilonewton is written. So the rest, all the parameters were written here. The load acting on the member, length of the member, diameter of this member, and so you can calculate stress in steel bar is equal to force upon cross sectional area. Force is 40 kilonewton upon area pi by 4 into 20 square. So directly I have written, and you simplify this, so you will get 127.3 Newton per mm square. Similarly, you write a free body diagram for member 2. So that is BC. So this is also subjected to a 40 kilonewton. So and one end is fixed. So it is subjected to reaction force. So that is acting in opposite of the force acting on one end. So left hand side, opposite of the left hand side. That is right hand side in opposite direction. Its length is 1000 mm. Diameter is 40 mm. So you substitute here. Stress in aluminium bar is equal to sigma aluminium is equal to 4000 upon pi by 4 into d square. D is equal to 40 mm. So you will get 31.8 Newton per mm square. So as usual, second step. So total elongation is equal to elongation in member 1. So this is delta L2, and in previous case that is delta L1. So total elongation is equal to delta L1 plus delta L2. Now you substitute delta L1 is equal to P1 L1 into A1 E1. So because here force is same force is acting. So on both the members, P1 is equal to P2 is equal to P. So therefore you can rewrite this equation. P you take common for simplification of calculations. L1, length of the members are different. So you retain L1 as it is. Cross-sectional area is also different, and Young's modulus is also different. So therefore, L1 upon A1 E1 plus L2 upon A2 E2. This is also same for second member. Now we substitute the corresponding values here. So load P 40,000, L1 800 mm, L2 1000 mm, and area pi by 4 into d square, diameter is 20 mm square, and into Young's modulus, that is 200 into 10 raised to 3. So it is written 2 lakhs. And similarly for A2 into E2, so for this part, so A2 is pi by 4 into d square, d is equal to 40 mm, and into 70 into 10 raised to 3. So that is 70,000 Newton per mm square. So thus, so after substituting the corresponding values in this equation, so you will get delta L1 0.5093, delta L2 0.4575. So total sum of these, total elongation occurred by this member is equal to 0.964. So this is one kind of problems, so which is subjected to one end is fixed. So either it is a uniform in cross section or variable in cross section. So the same procedure is adopted. So first we have to calculate stress and then change in length. So these problems are simple in nature, so which utilizes the same procedure. Let us see one more example. So this example is of a different category. So before starting with this example, so we'll have a overlook a little bit about this. So here, so in the previous cases you might have observed, so those previous problems, so this member, so I will take the highlighter. So this member, so there is no restraint or rigid body constraints are not put on either side. So this is not there in first case. In second case, it is there only on one side. But this is a third category problem. It belongs to this rigid supports. This is called a rigid supports are placed on both the ends. So these problems belongs to rigid supports placed on both the ends. Means there is no deformation. It will not, this entire section 1 and section 2. So both section will not move beyond this boundary. So they will retain within the boundary even after application of load. So here it is called a constraint. The moment is constrained here. So this is the third category of problem. So let us see. So what is expected here? See, a steel bar shown in figure is having a cross-sectional area 300 mm square. So this cross-sectional area for both the members is same, 300 mm square. Is held between two end supports. So this is one support and another support at A and B, and loaded by an axial force of 30 kilonewton. So it is loaded with a axial load of 30 kilonewton at point C here. Determine reaction at A and B and extension of the left portion. So here there is a similar way. So in the previous case, the load acting at different sections are known to us. So in this case, the reaction force, the force at supports is not known. So that we have to calculate. Such kind of forces are called reaction force. And the force of 30 kilonewton is acting at the center, and its length of the bar is given. Now in this case, so little analysis we have to do. So that analysis I will take this kind of problems so in the next lecture, but here for understanding just I will take the overview. So if it is subjected to load, this load, so this load exerts the reaction force opposite direction at this fixed end. Here reaction force, one reaction force, and at the other end also. So here only I will write this is the reaction, second reaction force. So in this member there are two reaction forces acting, and the number of elements 1 into 2. So number of elements are 2, and it's having a degree of freedom is 1. And so here, so number of reaction forces always less than or equal to, so 3 times of n. So when n stands for number of links, so here n, if you are taking this as a n is equal to 2, 3 into 2 6. So here, so we have equations only, sorry, support reactions 2. This support reaction should be always less than. So in that case, so such kind of problems need some additional, what I can call additional equations to solve the problems. So such kind of problems we will take in the next lecture. So that kind of problems are called determinant and indeterminate. In case of a determinant, number of unknowns should be less than number of equations, and in case of a indeterminate, number of unknowns are more than number of equations. That kind of problems we will see in the next lectures, determinate structure and indeterminate structure. But here, so what I mean to say, so this problem is of different nature. It is subjected to two supports and two members. So in such cases, two supports means there are two unknowns. So for solving these unknowns, at least we need two equations. So then only we are in a position to find reaction force. So for that, so first of all, we have to apply a equilibrium equation. So by using equilibrium equation, so we can compute or develop a equation. So that equation is called, say, summation of forces acting in horizontal direction is equal to 0. So this is the one equation, equilibrium equation, and this member is not subjected to any moments. So if there is a moment, and we have to consider moment also, so in this case there is no moment, simply the force is acting along the axis of the member. So therefore it creates reaction forces at supports only. So therefore there are two supports, RA, there are supports at A and B, and the reaction force, corresponding reaction forces at support A is RA, and reaction force at support B is RB. And whatever RA plus RB must be equal to 30. So according to the superposition theorem and equilibrium equation. So here, so by using that, sum of the forces acting in horizontal direction is equal to 30 or equal to 0. RA plus RB, here you can write this equation, RA minus, sorry, RA plus RB is equal to 30. It is acting in opposite direction. Okay, this is the equation is right. So thus, so we will get a equation 1. So there are two unknowns, RA and RB, because it is asked to determine reaction at A and B. So for that, we have one equation and there are two unknowns. So for that, what we have to do, we have to use one more equation. So one more equation, one equation we obtained from the equilibrium equation. So already we learned in the introductory lecture, there are different kinds of equations. One is equilibrium equation, second equation is constitutive equation, and third equation is compatibility equation. And constitutive equation is used to predict the behavior of the material, and compatibility equation, so it shows the conditions are under which the entire frame works. So those conditions we have to use. So here see, so before solving we have to write this in terms of given data. So already it is written. And the second equation is, so we have to write a compatibility equation. So compatibility equation for this, so because this end is fixed and another end is also fixed. So if it is fixed means, so due to application of this load 13 kilonewton, so this member, see here, this is reaction force is acting in this direction and this load is acting in this direction, means this member is subjected to compressive load. It will undergo deformation definitely, But how much it will undergo deformation? Say this is the amount of deformation it has occurred due to application of compressive load, and same amount of deformation so occurred by this material, aluminum material, because it is subjected to tensile load, means it elongates and it compresses. The elongation in this steel bar is equal to the elongation in aluminum bar, or extension of amount of extension of aluminum bar is equal to amount of compression of steel bar. So you can represent this in any way. So this is the one compatibility. By looking at the configuration, so we can assume that so this has a one compatibility. So amount of decrease in length is equal to amount of increase in length. So by using this equation, so we can write so this compatibility equation. So that is delta L, total change in length, because this is the rigid. So total change in length is equal to 0, though they have undergone independent deformations. So total change in length is equal to 0. So this is a change in length in AC. So RA LA into AE, delta is equal to PL by AE. P is here, so we are assuming RA, and similarly delta change in length. So in second member, BC is equal to RB into RPL by AE. Now substitute the corresponding values. So you will get the equation in terms of RA and RB. 300 RA plus 700 RP. So here we have substituted the values. L is 300 mm. So this is 0.3 meter converted in terms of mm, and 700 mm. So this is 0.7 meter, and 300 area of cross section is same for both the things, 300 mm square, and Young's modulus E for aluminium is 0.7 into 10 raised to 5, and here it is 2 into 10 raised to 5, or 70 into 10 raised to 3, 200 into 10 raised to 3. In previous problem we have written like this: 200 into 10 raised to 3, 70 into 10 raised to 3. So one and the way, one and the same. So either you represent like this or that way. So don't get confused with these values. So both have same. Now we will get the second equation. Now you solve these two equations, equation 1 and 2, simultaneously for obtaining the values of RA and RB. So RA, RB. So to solve simultaneously, this first equation is multiplied with 300. So you will get this is 300 RA plus 300 RB is equal to 30 into 300. So that is, so you change the sign. This is minus, minus, and here it is minus. So this get cancelled. 300 RA, 300 RA. So here 300 RB. So this is positive. Minus 700 means minus 400 RB. So here 30 into 300. So it is 9,000, and this is 0. So you will get 9,000. Now you can compute RA, reaction force RA is equal to 9,000 upon 400. So it is 22.5 kilo Newton. So here there is a sign convention, negative. So negative represents acting in opposite direction. So that of the previous one, 9,000 is acting in this direction. So this force is acting in opposite direction. So similarly, RA is equal to RA plus RB is equal to 30. Then RA is equal to, sorry, already it is RA is computed here. Sorry, this is RB, not RA. So this is RB, and RA is equal to RA plus RB is equal to 30. So this is equation we have derived previously. So by using equilibrium equation, now you substitute the value of RB here, and you will get 7.7 kilo Newton. So this is the amount of force RA and RB we have computed. This is first task. Second, extension of left portion. Extension of left portion, that is aluminium. So this is the left portion. So here you can see aluminium. RA into L upon A. RA is 7.7 kilonewton, and so this is kilonewton. So it is converted in terms of Newton multiplied with 1,000. And here L is the length of the member is 0.3 meter, 300 mm, and area is 300 mm square, and its Young's modulus is 0.7 into 10 raised to 5. After substituting this, so and simplifying, so you will get the total extension of 0.11 mm. So thus, so you can obtain